How's it going for you?
It's alright, like, I haven't got into the main part yet.
Gotcha.
Yeah.
I'm not seeing it. This is just a monitor.
Yeah.
It's. Okay, it's 4:30, but I think we'll probably give it another 5 minutes if people are still like walking in and stuff, so. It's recording.
Yep.
Okay. Yeah, let's give it another 5 minutes. You have Elixir pulled up with those macros, the logbook.
Doesn't need this.
I guess.
I have given the macro definition in tables.
Did we have our virtual machines pulled up off to the side during this?
You can. We might move a bit quick for you to follow along, but these slides, we'll probably put them on Canvas, right?
We'll have to.
Yeah, we'll put these on Canvas.
Maybe.
We're gonna
We don't
record.
know yet.
Okay, we might, this is being recorded, so if you wanna go back and revisit something we talked about. You
Okay.
should be able to.
And if you
Awesome,
want,
thank you.
if you
Yep.
also want us to stop somewhere, if you're trying out something, feel free to let us know. Like, can you guys wait for 5 minutes to try something, whatever we talked about? That's okay as well. And as long as we can finish the session in 1 hour, we are good with it, right? So that's our priority. So yeah, let's start.
Okay, so, this is me, I'm Alex, this is Chris, I am a TA for, Ming Zhao's in-person session right now, he's also helping and, we are here today to show you some utilities that the kernel offers, some options, things that it presents to you, to help you debug, as these projects get more complicated. Any questions before we start? Okay. So, like in user space, bugs in the kernel vary widely. But, since we're working in kernel space, there's a lot more consequence. And they're also a lot harder to debug. So they can appear for many different reasons, from incorrect code, this could be, logic errors, etc. Synchronization issues, with the emergence of semaphores in project 3. It's very likely you might encounter these types of issues, which Yeah, and since we're, working in kernel space, it's a lot lower. Thank you, yeah. It's a lot more lower level, so there's also hardware management at a lower level versus in user space. And yeah, ultimately these bugs can manifest themselves in have many different side effects, from poor performance to incorrect behavior. And yeah. So to explain a quick example, something you might experience, imagine, with project 3, we're introducing kernel threads, right? Because it's process management. So one thing that could happen is, you share data across multiple processes, right? One process might free said shared data. Another process might attempt to use it after free, leading to a use after free bug. Depending on, what the first process does after freeing it, it could nullify the pointer or leave it. So this will ultimately lead to either a null pointer dereference or dereference of a pointer pointing to garbage. Both lead to issues, right? If it's a null pointer dereference, this will result in a kernel oops. We're going to talk about those, how to read them, utilities for interpreting these kernel oopses, and pointers to garbage are weird. It's undefined behavior. It might still run just fine and lead to corruption, but yeah. So the first option, this is probably what we've all defaulted to in the past, is using print statements. This is the simplest way. So if you're familiar with C, you've probably used printf. Print_k is in many ways similar. The F in printf stands for format string. That's because printf's first argument is a format string. Same thing with print_k. So you can have in quotes like a %d%, any basic format string that exists with printf will probably exist with print_k. So this is nice. It's utilitous. You can call it from anywhere at any time. You don't have to hold any locks. Additionally, there are certain things you shouldn't do with locks held. For example, allocating memory, freeing memory. This could lead to issues, but you don't have to worry about this with print_k. It doesn't matter what locks you have held. You can call it at any point. So it's convenient. There is one major difference between printf and print_k, and that is with print_k, you have the option to specify what we call a log level. And this is done with one of multiple macros. You can see there are examples at the bottom. This is just a few of many. We'll show a full table later on. But and ultimately what you can do is you use dmessage to see the output from the kernel, right, in the kernel log. And after providing some additional flags to dmessage, you can actually filter based off the log level. So we'll show you how to do that. So as shown on the previous slide, we had kern warning, kern debug. These are two of many macros specifying different log levels. And ultimately they expand to something that looks like this. It's just a number in a traditional C string. And the intended usage is if you don't provide this, it'll go to kern default. But if okay, I'll get there. This table just shows all the different log levels. I'll give you a sec to look at that. So there's one for errors, alerts, critical conditions, warnings, debug messages, etc. Yeah.
So just to add a little bit over here is like how you have been coding previously, right? You just log all the errors under one hood, right? So what kernel is trying, or what we're trying to tell you over here, log level, is to, understand the severity of different issues. That is why if you see by the nomenclature, some are like alerts, right? Something bad has happened and the developer should take immediate action, right? Some are just, let's say, information. You need to log some messages. Like, for example, when we give you grading scripts, it dumps a lot of information, file found, whatever, whatnot, right? So these are just generic information. This has nothing to do with an error or, some corner case that needs to be handled. So this is very important how kernel in itself, tries to differentiate between so many messages that kernel just dumps. Not because you have seen those logs, So you have seen the intensity at which, these plain text logs or messages are dumped. So this is one way to differentiate between those and understand the severity of other messages. Yeah.
Any questions? Okay. So we have a example kernel module here showing the intended usage. So it's just no comma, you just prepend the macro to your format string and whatever arguments follow it. So you can see we have one with kern warning, one with kern debug. If you run dmessage as it is without any arguments, it'll print everything, right? Whereas if you, let's go to the man page for dmessage. So here we're doing dmessage minus L. If we look at a man page to see what that is. Scroll down, it's near the bottom. Yeah, level. So this restricts the output to a given comma separated list of levels. And again, this list of levels will be again comma separated, but it's a list of integers that correspond to the different log levels, right? So if we go back, we can see here we're doing dmessage L minus L4. This is the specific log level number we're warning. So you can see that it filters it just based off of the warnings. Same thing, we provide 7. Shows debug messages, and you can provide multiple to show multiple log levels at once. Does this make sense? Okay. So the kernel also provides, I think, yeah, these are macros, which are basically just wrappers around what I just showed you. So this is print k with one of these log level macros. And then this middle column here, these are wrappers around it. So to show you what that would look like, intended usage, it's just PR alert or PR notice. Again, alert and notice are 2 different log levels, followed by the format string and whatever arguments you want to feed to that format string, right? So, and you can see similar thing with dmessage minus 1, it behaves just like what we showed you in the previous example kernel module. Does this make sense? Just another option, a little more concise.
You guys are familiar with what is a macro, right? Okay, cool.
Okay.
Yeah, so as of now, what we have covered is, how we can do some initial debugging using printk, right? And as of now, you have already understood that kernel just dumps a lot of information on different severities, right? Now we'll try to understand how this information is maintained by the kernel, where it is being dumped, and how it is internally managed, okay? So all throughout, kernel makes use of a circular buffer. And as it's implicit by the name of the circular buffer, that it logs messages in a circular pattern. So if let's say that the only disadvantage of having this design is, let's say if the buffer is not flushed on time, you might lose some messages, right? But the simplicity that it provides. So one thing we should always keep in mind is that kernel or even everything in operating system, the designs are very simple and easy to follow. Nobody wants to create any complex designs, right? Because there's so much modules and internals going on at the same time, right? So similarly, coming back to this, log buffer is the simplest approach to manage entire logging, which kernel maintains and also facilitates user space or user programs to manage those. So as the slide mentioned, that it has multiple advantages. That's easier to simultaneously read and write from a circular buffer, right? And the other advantage of is which you might be covering in your lectures as well, that interrupt context, process context, in all these different contexts in which the kernel operates, the printk is able to still work on these. That's the robustness of using printk. So that is why we started with debugging using printk, because it's one of the most robust ways to do any kind of debugging, right? And as mentioned, the only disadvantage of using a kernel or a circular buffer is to a possibility of losing some messages if it's not flushed on time, right? And trust me, if it's managed well, the probability of having such a corner case is very small that you will lose some kind of messages. It's so well designed. So to facilitate these, there are a few daemons in the kernel process, in the kernel, sklogd and syslogd. Okay, So klogd is a daemon which retrieves the kernel messages from a buffer. So if you try to imagine there's a buffer line somewhere, and daemon is nothing just but a background process. You can think of daemon as a background process which starts as soon as you boot up your machine. Okay, so just imagine there will be some time, taken by this process, or let's say this daemon process to start up and start to do its job, right? For example, in project 3, you are starting some kernel threads, right? So until unless you insert the module, the kernel thread won't start, right? So similarly, when you boot the machine, it will take some time for these daemon processes to start. So what happens is all the information is dumped into a circular buffer, right? And those informations, when these daemon processes are up and running, they will go and read the messages from this circular buffer and dump it forward into plain text files. So that is what klogd does. It retrieves the kernel messages from the log buffer and sends them to the syslogd daemon. So these are two different daemon processes. And from where klogd reads these messages, so there's a proc file which is called kmessage, kernel message, right? So all the messages are dumped into this file. And this is you can think of this as a data pipe, which essentially means that once the data is read from here, from this file, it is no longer present there. So now it means that now you have read that and there's no need to keep that data redundant data in these files. So another property of klogd is that it just blocks until there are new messages. And whenever there's a new message, the daemon process wakes up, read the messages, and then send these messages to syslogd daemon, right? Another important thing to notice, to keep a note of, is the syslogd daemon, when it receives these messages, it appends all these messages into different log files, right? Now, coming back to what we were talking about, that because kernel is at a very supervisor mode, right? It tackles kernel mode, user space, everything around it, right? So what it does is it can filter, and this is a configuration which we'll talk about, but to understand, it filters out and keep important messages in separate files, such that it's easier to maintain by the Linux administrators, easier to understand, right? And this is where even log levels also play a very important role. For example, a default file that you will find is var log kern.log. So all the log messages that kernel maintains can be found inside the directory var log. Okay, so there's a file kern.log. So this is nothing but just kernel messages of any log level. Right, so you guys can try different log levels, and that is when you do a dmessage, or in our previous examples, when we were doing dmessage and still logging different log levels of messages, you could still see warning, info, all these different alert messages or different log levels were present in the dmessage, because it's nothing just but a kernel message, right? Or kern.log is nothing but just dmessage, okay? The other is var log syslog. So it also logs everything except any authentication messages. For example, a system can have multiple users, right? So if somebody is logging in and the authentication process is enabled to, authenticate a user before, or a user to log into your system, those messages are not part of syslog. They are maintained in a separate file, auth.log, which is also present in var.log directory. Then there's also var log messages, which actually dumps everything. It stores non-debug, non-critical messages as well, right? So you can think of it as a superset, right? Which is dumping all the system activity in a log file. And as explained above, it's facilitated by the syslog daemon. Okay. Any questions over here? Any confusions? No. Okay.
Can I ask, if
Yeah.
you wanted to try to utilize some of the, basically the message to see, for project 3, what are some methods we can do to check, to make sure that project 3 is running all those messages? Because I was running into some errors when I was testing, and I couldn't seem to figure out how to see the kernel log.
So when you are, so for all the project related, if you are following our project document, we always give an example of dmessage in our project documents. And as we just explained, dmessage is nothing just but var log kern.log, right? So what you can do is, first of all, there should not be a good reason why messages are not displayed in dmessage, right? it essentially is and it's because it's a circular buffer, the only reason that it's not there, maybe it's not flushed into the buffer yet, right? And that is why, if you remember in project 2, some people were facing issues if there was not a \n in the print K, you were not getting those messages in the D message, right? So the other log file I would say to track is var log kern.log, because essentially it records kernel messages from any log level. So, and it's essentially the output of D message. So that should be one of the important places to look at least for all our projects.
And all I have to do for that, should I be in the folder that holds all of the project and then just do the var.log.kern?
No, you can do it from anywhere. So let me show you, for example. So essentially I can open the file here as well, var log.kern.log. And we will also show you some, utilities, how to manage, like, some manipulation utilities, how to manage these big log files. How, like, for example, we are doing D-message filtering based on log levels. We'll later cover a small few utilities which will make your life easier when you are dealing with these logs, which are maybe big in size. And if you're dumping a lot of messages while debugging, the size of these log files essentially increases.
Go back real quick.
Yeah.
Just a quick note, if you run sudo dmessage, that'll show everything that's been logged since boot, right? This is persistent. So if something goes wrong and you have to reboot, you can go back, look at this kern.log and see.
Yeah.
Yeah.
Do you always have to use sudo?
Your voice did break, but I think I understood your question. Yes, you have to always use sudo. Yes.
Okay, thank you.
So one thing that we should always keep in mind is that kernel is always evolving, right? If you go and track like, for example, in this project, we are working with kernel 6.10, right? And the new versions is still coming out, right? So it's always updating, getting better day by day, right? So now, as we talked about syslog-d, a newer advanced version of syslog is rsyslog. Okay, and as far as you guys are concerned, you should not be, you should understand the motivation of these different utilities rather than as of now to understand how they're actually, or what are the different different utilities for the same purpose. So to rephrase that better, rsyslog is just an advanced version of syslog, and in the latest kernel versions, you might see rsyslog configurations rather than syslog configurations. And if you go back and read on internet, you'll see how syslog has been, advanced to rsyslog and how it is better and other stuff. So now, in this entire slide, the most important thing that we want to point out is this box towards the end. So what this is just showing is a snippet of a configuration file. So this is just to let you know that everything in kernel you can configure, because you are the sudo user, you are the, you have all the access, you have the root access to configure everything, right? And for every utility, there is some configuration file on which these daemon processes or these utilities rely upon. So for example, this entire logging, which is managed by rsyslog, there is a configuration file which states what information will be dumped in which particular file, right? For example, out here, it shows that, okay, kern.star, this is logged in var log kern.log. And this is, you can change this. You can, if you want, you can redirect it into your own file, right? And it will keep on doing so unless you ask the daemon process to update or, change the default location. When you, for example, let's go back to the terminal real quick, and just to show you, there's a lot of different kinds of log files, for example, kern.log. And this is another good example to see how it is a circular buffer. You can see, once the kernel.log, the size of that log file is whatever is the limit that reaches. So it goes on and creates log.1. So if you're dumping a lot of information and you cannot find your prints, you're debugging a lot. It won't happen in CSC 330 projects, but a general suggestion. You're dumping a lot of debug information, right? And you cannot find it in your log file. So what you can do is you can go back to previous log, log 2, log 3. That is how that circular buffer is being maintained and broken down into multiple different chunks of file. Okay. So out here is where you see these different, all the different log files present, and each log file serves its own purpose. Like there is a mail.log if you have some SMTP server configured in Linux, so SMTP is nothing but just a mailing protocol. So something like that. So all those information are dumped there, right? Any daemon related information is dumped in var.log daemon. So for our sake of purpose of our projects, right, we'll be majorly focused on kern.log, which is same as dmessage, right? And maybe var.log syslog, but for the scope of CSC 330 projects, everything that you need to do or any kind of debugging that you need to do, var.log kern.log is enough, to complete any kind of projects. This is just let you know what are the different other log files available and what are the purpose of those log files. Any question over there? Okay. So this is just an example of how you can even, append some messages into these different log files. For example, out here, what we have tried to do is we have tried to use this logger utility to dump a message, hello CSC 330 students, right? And you see when we do a grep, so we'll get into the details of what is a grep, but essentially it's like, doing a control F on a file. You want to find something, right? In a big file, you want to find something. That is what is the utility in Linux. You can do so by doing a grep. So you're trying to look up for something. And what we're trying to look up for, we're trying to look up for a string called hello CSC 330. And where we want to look this message or which file you are looking into is var.log syslog, right? So as you can see, this message was found. This is just an example that how even from a shell, you can, append some messages into these log files. And this is just a proof that yes, this works and this happens, okay? So now specifically talking about dmessage, because you guys have been extensively using dmessage, right? So dmessage stands for diagnostic message. It's just a command, again, which just prints the kernel buffer or the buffer of the kernel, right? And for an analogy, again, it's just var.log kern.log that you are seeing when you do a sudo dmessage, right? One important thing to note is it's also include messages by the device drivers. And as of now, to understand device drivers, you can only think of, a chunk of code which is responsible for some devices for on your system. For example, you have audio devices, you have network cards and everything else, right? USB. So every utility that is available on your system, it has a set of code which enables and provides these functionality to the users. So you can think of, as of now, you can think of those as device drivers. So everything which is happening on your system which is being taken care by kernel, everything is being logged here. Another important thing which at times people miss on is that you can also not just examine the control buffer or sorry, the ring buffer of the kernel, but you can also control it in few ways based upon the different utilities the dmessage provides. For example, if you had tried dmessage -c, so it's just a command line option to clear the dmessage, right? So that is how you are taking a little control on these ring buffer, on these kernel ring buffers, not just examining them, but also controlling them in some ways. Now, this is what we were trying to hint previously that, and you must have seen in these are examples as well, that dmessage or even these big log files, there are some manipulation tools like tail, less, grep, right? And these are very common Linux utilities which are extensively used in Linux when you are dealing with log files or, any kind of file which is, let's say, you can even do this on your code as well. So it works with any kind of file. So we'll have examples for this, but just to give you a quick heads up. So tail just nothing means, it will try to read a file from the end, right? And it will show you the messages towards, let's say you say tail -n-5. So it will show you the last 5 messages from a file, right? And you can keep that active, and as the messages grow, you can see them on the screen. grep is just to look up for something, like a control F, like how you do on a file. Less is nothing, like, for example, you have a file which has 10,000 lines, right? But you don't want to see all the 10,000 lines at once. You want to see 20 lines, 50 lines, because you want to really dig deep into these log files to see what is happening, right? So that is where a utility like less is helpful, where you see these big log files in chunks, like 20 lines or 50 lines, whatever. So now this is where we show an example of how we use these manipulation tools. For example, sudo dmessage. And this is how we use in Linux. This is how we use two different command line utilities together by piping them. So if you notice at this operator after dmessage, this is a pipe operator. So essentially what it's doing is sudo dmessage, and on the dmessage it's also executing tail minus n15. So what it is doing is going and printing the D message, but only printing the last 15 lines. Why last? Because it's tail. So from the tail end, it's printing the last 15 lines, and you can definitely count, it cannot be more than 15. The other example that we show out here is how you can use grep with D message. So essentially you do D message, and then you try to look up for a message, not a useful print, right? And as you can see, it will just filter out from the entire chunk of the log file, and it will only filter out those lines where it is able to match that particular message.
This behavior comes from the -v flag that specifies specifically filter everything related to, this string at the end here, not a useful print, exclude anything that matches that string.
So, yeah,
Does B mean anything?
yes, as he explained, it's like excluding.
Yeah, but is it short for something? Or
Check
is it
command
just that
page.
they have allocated B to exclusion?
Okay, so yeah, that is something. I'm not sure if -v stands for something.
Yeah.
Yeah, so that's a good a very good example. That's a very good way to understand anything. So in Linux, like for example, like how we were just showing you. So anything, if you don't know any command, how to use a command, right? Obviously, you can go on internet and read about it. But the easiest thing to do is, let's say man. So man stands for manual page, okay? And you write the name of the command. So man grep. So what it will do is it will open up a manual page for that command, which not just explain or it has a description for the command, but it also gives you all the different arguments that this command can receive. For example, -v, -v is for invert match. So that's, this is something we learned today, right? So for example, if you want to ignore the cases, so that's like -i. So you can, search accordingly, create your text based upon your utility that you're doing. So yeah, now what if we do, so for example, when you are working with your projects, especially with, let's say, project 3, right? Because things starts to get real in real kernel development from project 3 onwards. Project 1 was like kernel compilation, getting to know how to compile a kernel. Project 2 was creating a system call. And now with project 3, we are getting into process management, right? So if you have read the document, you will see that each thread is printing some message, right? So let's say you start 50 threads, right? And you're tracking these messages. So one way to do so is you can start your D message and have tail -f. So what it's essentially doing is this command line utility will not exit. So as this arrow shows, as and when there's new print in the D message, there'll be a new line that you can see. So it's like, if you have used a watch command, which updates every second, right? It's on a very similar note where essentially the updates you can essentially see on the shell as the updates happen in these log files. So as and when a new message is read now you understand in the background what is happening. As and when a new message is read from the kernel buffer, passed to the syslog, the syslog daemon, it appends into a file, you can literally see it on the shell, right? And try it out. It's so quick. You won't see that there's so much pipeline behind it. And that's the advantage of having simple designs in kernel.
And the F stands for follow. I know that one.
F stands for follow, yeah.
Follow output. Something like that.
Any questions? Anything that you might have tried with these different messages? Anything around your project work that you think might be helpful? Any questions on that? Not in person. I don't think any questions online.
No, we're good.
Okay, so now we'll get into more details of actual errors and how we look at those errors, how we understand what's happening. So
Okay, yeah, so earlier I mentioned kernel oops, and I explained like an example error you might see in a kernel module and how it could potentially lead to a kernel oops. So what a kernel oops is, it's basically the kernel's way of saying something went wrong. When this happens, it'll print a bunch of stuff. It'll appear when you run sudo dmessage, it'll appear in the kernel log, etc. And it'll show multiple things. I believe it shows like the actual machine code. Probably don't need to worry about that. The registers probably also don't need to worry about that. But a particularly useful thing is it'll show a call trace. So if you don't know what that is, basically it's just, oh yes, if you remember to stay close to the mic. A call trace is basically just the sort of hierarchy, or basically it's the stack, the list of functions that appear on the stack. So if I had a kernel oops in so-and-so function, what functions did I call to get to this point, right? Does that make sense? Okay. So here's an example. So this is a kernel oops that was triggered because the machine was in idle. What is this example doing? And yeah, so the CPU is idle, a timer interrupt was fired, and this timer interrupt appears to have triggered a null pointer dereference. So sometimes it'll also mention, you know, what went wrong. So here we can see null pointer dereference. And this is the call trace I was talking about earlier. So over here in the sort of description of what was happening, we had CPU idle, which called default idle. We can see these functions in the call trace, right? So CPU idle, default idle, eventually the timer interrupt occurred, etc. Right? I guess that would be a good time to mention, since we have an example here, the higher something up is on here, the more recent it is, right? So this was the last place we stopped before things went wrong, right? Yeah, so looking a little deeper into the call trace, you can see that it actually has function names, right? So there's function names plus some number. This is an actual offset into this function. And later we're going to talk about how to interpret this and basically determine what line of code this comes from based off of this output, which is particularly useful. So a nice way to prevent stuff like this from happening is, or to debug stuff like this, is just trying to prevent it from happening entirely, right? Does anybody use asserts in their code? You know, assert's a pretty widely used thing. Python has it, C has it. No? Well, basically, if you say, and same applies across Python and C and other languages, I'm sure. You say assert, you call it like a function, and you pass a Boolean expression. And if that Boolean expression evaluates to false, it will, and I'm specifically talking user space here, just to associate it to something familiar. It'll kill the user space process. So in the kernel, you have similar mechanisms. You have bug. If you call bug as a function, that will just lead to a straight up kernel oops. It'll tell you what line it was called on, etc. And then you have bug on, which I like thinking of as an assert. You have to be a little careful because bug on, like assert, takes a Boolean expression, but it will generate a kernel oops and spit out a kernel oops when that Boolean expression evaluates to true, right? So bug on when this happens, right? So it's when it evaluates to true. Yeah, this unlikely statement, it wraps the assertion in an unlikely statement. This is basically just like a really low level optimization. You probably don't need to worry about it. And yeah, any questions? Yeah.
I'm kind of confused on why you would want to use trigger kernel oops and then how you would interpret the result of the output.
Yeah, so let's say, I'm gonna talk loud so the mic can hear me. Let's say we have like a global variable or something. Or it could be whatever number. And at some point, we wanna make sure it doesn't cross like some threshold, right? That would be like a perfect place for a bug on statement. Like we have a for loop, we wanna make sure that if I is an index or something. And we wanna make sure it doesn't exceed the boundaries of some buffer before we do an access. That would be a perfect place to use bug on, right? Because you can do I greater than equal buff1 or something, right? And then at that point, it'll spit out a kernel loops, which will show like, okay, it'll spit out a bunch of context, like what function was I in? What did I call to get here? Stuff like that.
And to add on to your question, so it's important, especially during development and also during deployment. If you were tracking the recent CrowdStrike issue, which left us our laptops and all the devices not working. Essentially, it was the code trying to access some invalid memory, right? But if you were designing your or if you were coding your functions, your kernel modules well, so the range of the memory that you should be accessing, right? So if that particular developer had these checks, so essentially it's called negative programming. Essentially, you are trying to think of all the use cases where your code can fail, and before it's deployed or in all the testing, it can be revealed. So if you have these bug on statements, your kernel or your process execution would stop there, would halt there, rather than trying to go ahead and do something which would cause other issues, like what happened with CrowdStrike, right? So that is how it's very important. These kind of bug on, and even in user space like asserts, this is where one developer is being differentiated by the other developer, how well you can code with usage of these other utilities to make your program more robust to errors and easier to identify those errors, right? Just imagine not having a bug on and something weird happens.
Sneaking by.
And you cannot find what is the actual reason behind this. But if you had these corner cases, these validations, you would literally able to pinpoint, or this is the reason why, or most likely the cause of whatever unexpected behavior. Because as we mentioned, errors in kernel, they manifest in different forms. So it's important to understand what is the root cause of a certain behavior. Yeah.
Okay, so here's another example kernel module. We have a function here, and it's pretty similar to what I drew on the board. We have int bar, and here we have a bug on statement to make sure bar equals, we check that bar equals 0. If this happens, it'll spit out this, right? And you can see in the demo in it, we pass 0 to foo, which triggers the kernel loops. So, yeah, that's a good point. It also, you can see on this line here, it says where, like which bug on statement was triggered. So you can see example.c line 12. It doesn't have the line numbers, but you can imagine this is line 12, right? So going back to, standard C libraries, there's assert and there's static assert. Similarly, there's bug on and there's build bug on. If you don't know what static assert does, it's basically an assertion that's done at compile time. So here you can see I have a similar thing with build bug on, right? Where I'm passing 0 to foo, but this time it's build bug on, and now this won't even compile. So this is basically just like, something you can include to make sure that initialization steps are being done properly is probably the best use case. And yeah, you can see this is the compiler error. Yeah, compile time assert, example.c line 5, build bug on. Yeah. Makes sense? Okay. Panic is something to be used cautiously. You probably won't need to use it for 330, but basically this is just something to call when something absolutely critical, really bad happens, right? So you can see here, I mean, this probably isn't a big deal, bar being equal to 0. It's probably not worthy of a panic, but we're doing it for demonstration purposes. this will just completely halt the kernel and yeah, we don't really have any output to show for this one because the machine went unresponsive. So this is just for like severe cases. We need to stop what we're doing because damage is being done, right? Yeah, so another useful utility is, and you may or may not find it useful, but we mentioned it anyway, is if you're curious to see like where a function is being called from, you can include this dump stack function. This is an actual function in the kernel itself. Next slide, yeah. And you can see that's sort of what this looks like. I have an example here. So you can see, we have a function bar. Let's say I want to know where bar is being called from, and there's like a hierarchy of functions being called leading up to this point, right? We have demo and it calls foo calls bar, and then bar calls dump stack, right? And we can see this reflected in the stack trace that it outputs here, right? We have demo init, foo bar, a lot of stuff you don't have to worry about. You can see in these square braces, it says example. This is the name of the kernel module. So like, just some advice, you might want to look for this when you do this kind of thing, but yeah. And this is particularly useful. So earlier I mentioned regarding kernel oopses, there's in the call trace, there's a function name with an offset, right? And that was some hex value. It's not very easy to translate it to a specific line number, right? Especially if it's like a long, complicated function, it might not be so obvious. So f-adder to line, if you guys did project 1, is something you guys already have. It is a script that is provided with the Linux kernel source, which will take, the lines shown in the call trace and convert them to actual line, like specific line numbers in the code. So, works with inline functions. And what's really nice is it works with kernel modules. So we have an example. You'll have to forgive, we couldn't fit it all vertically. So it reads top to bottom, left to right. So we can see this is using kernel threads, right? As you will in project 3. So here we're starting a kernel thread based off of this function. And if you know C at all, you will know that this is a terrible idea, right? You don't want to dereference a null pointer. But for the sake of demonstration, let's say we don't realize we're doing this and it's not obvious that this is happening, right? So we in smod load the kernel module and we see this happens, right? So this is a kernel oops, and specifically we're looking at this line here, right? So my kernel module name was demo. And the reason why I picked this line specifically is because, well, number one, I know that this is a point, this is in my kernel module, right? Because it has the name here, but it's also the highest up. So typically I think it's probably best to start higher up, work your way down if you need to, because with this, I know that this is the last point in my code. This is the last place I was in my code that I was, the kernel was running, right? So again, this is probably hard to read. This is just the same thing, but enlarged, right? So things went wrong in demo k thread function plus this offset, right? It makes sense why I picked this line, not some other line. Okay. And so yeah, as I mentioned before, f-adder to line, you have this already. It's a shell script. So for project 1, we asked you to basically download the kernel source, right? It came in a zip file. And if you go into that resulting directory, there should be a scripts directory where you will find this script. It takes 2 arguments, one being the actual kernel object.ko file itself, followed by what I showed on the other slide. Right? So this is the function name plus the offset. And you can see in this output here, it says, okay, this is the file where things went wrong. Here's the line number. And if we look back at the code shown a few slides ago, we can see it tells us exactly where things are going wrong. Right? Does this make sense?
And this is the utility which will be more, apart from all the logging utilities that we discussed, this will be a utility which you can extensively use from project 3 onwards.
Yeah.
If you don't understand what is going wrong, where, a problem is in your code, with the oops, with the call trace, now you will have a line number in your code, right? And then with extensive debugging prints, printing different pointer variables, their references, you'll be able to figure out what is being messed up, out there.
Yeah. So I think the next thing is KGDB. Yeah. So if you want to take it a step further.
Yeah, so as of now, what we have been discussing is like very simple utilities out there to make sure the kernel is working or our code is working as expected. But at times, these are just not enough. And most important thing to point out is in the scope of our CSE 330 projects, you don't need a KGDB. But our intention out here is to also expose you to different utilities available in the Linux, right? Maybe you don't need it for CSE 330, maybe you need it for some 400 level course later. So it's important for you to know what Linux has to offer. That is why we told you about dumpstack, and that is why we're talking about KGDB. So it's nothing but just a source level debugger. If you have used GDB in a user space program, every programming language offers it. C++, C, Python, every programming language out there has a GDB. And GDB is nothing but a generic debugger or a GNU debugger, right? So essentially what it does is it helps you to, so as you already know, your context in the program executes line by line, and it differs programming language to language, but for the sake of argument, let's say it's executing one line at a time, right? And you want to stop the execution at a certain place and inspect what is going on in the code, rather than giving print statements, waiting for a code to fail, and then realizing what has happened, going back, giving more prints, and running them again. If you need to reboot your VM, doing all that again and again. So this is where a utility like GDB is very efficient when you're doing code which is, let's say, more than the scope of your CSE 330 projects, right? Where the code is thousands of lines. So essentially what you can do is you can place breakpoints in some kernel code and have execution stepping. So execution stepping is nothing where you, like how the code actually is run line by line, one line at a time, or one instruction at a time, right? To be more specific. So you can execute your code line by line, and you can inspect what's going on in this certain line. Then you proceed to the next line, and that's how it's an efficient way to debug. Okay.
You can inspect any memory location,
Yeah.
any variable, etc.
You
That's something you don't get with fadder to line.
Right. So you have, because you have loaded the entire binary, all the system tables, everything is loaded, so you can inspect anything that is being required by that certain code to successfully run. So to give a short or a quick way how GDB is used is essentially to use KGDB with these VMs. You need two machines. One is your development machine and one is your target machine. Okay, and it requires a series of steps to enable the GDB, right? Use it to serial port or serial console, right? So what we have done is we knew that we might not be able to cover this in this entire session. So what we have out here is a YouTube video that we have embedded in the presentation, right? And this YouTube video, it talks about the entire process of setting up a GDB and how to use GDB to, to do some kind of debugging. Again, this is an advanced debugging process or whatever you want to call it. So if you're concerned about your CSE 330 projects, you essentially don't need KGDB. The other ways that we have exposed you to, like, print K, the fadder to line, the other bug on and other stuff should be good enough for your CSE 330 projects. If somebody want to go ahead and, try out the advanced debugging techniques, so KGDB is one of those ways. So when we share this with you, you'll be able to have access to this video recording, go through it, and if you're interested, set it up and try it out, right? I'm sorry. So yeah, I think that we are out of time as well, and that's all what we wanted to bring up, at least in the first session. We're not sure if we're going to do more sessions after this, but yeah, if you have any last minute questions, feel free to ask those. Yeah.
Just a general.
Yeah.
Will this PowerPoint be uploaded?
We'll talk with Dr. Zhao and we'll get back to you. Most likely it will be, but I can't promise you anything right now. Yeah. Any other questions? Yeah.
Would it be possible to do like an email list, something like that? Just to try and, just because I would really like this, just if that's possible. That's
Email
not-
list of?
Yeah, if, like we could all like write our emails down. or
No, if it
something.
is shared, it will be shared with everyone. No,
Okay.
no, don't worry about that. Like, if we are gonna share something, it will be shared with the entire class. That's good enough. Any other concerns? Anything on the online session?
I
Okay,
had a question, actually.
Yeah.
So earlier when, we were talking about, the like utilizing the message, you mentioned that it was also in the, project file. I don't know if I'm just blind, but I don't see anything of like what we can run for message. Is it built into the test module, sh?
no, so whenever you do a print K, right? Whenever you are doing and wherever in the code you're using a print K, right? So essentially that is written into this proc K message, and that is where the syslog D dumps into the D message. So any message that your kernel module is printing using print K or yeah, that's the utility in Linux kernel. So all those messages should be available in D message, right? And if not, obviously it should be there, but the other file that you can track is var log kern.log.
Okay, so we could just do the sudo dmessage and then we could probably just do tail.
Yeah,
That's
so yeah, sudo D message is like how you look at the content of the D message. Yeah. And what you can essentially do is you can also use the editor in Linux, like a editor like Vim, and open the var log kern.log, and inspect this as well. I'm sorry, there is no message that I can show you here on this Linux, but you understand what I'm trying to say, right?
Yeah, no, I get it now. I just make.
I see something happened, some seg fault happened somewhere, and that's being dumped,
Okay.
right? The
Okay.
administrator can go and now investigate this. Any other questions from online?
I don't have a question, but I just wanted to say thank you guys so much. I really appreciated this. Lots of good information.
Yeah, thank you. Thank you.
Other than Googling anything, is there a good online resource that you guys use to look stuff up?
That's a good one.
So essentially what we do is, obviously we make extensive use of Google. That's there, no point lying about that. Man pages is a very good utility to understand how to efficiently use a kernel, code. The other, I would say,
Elixir bootlin, Linux cross-reference, really good for just reading the kernel source
Yeah.
itself.
if you want to really see the actual kernel code, so we would suggest you going. So you actually have this code when you downloaded that tar file, you actually downloaded the entire Linux code, right? So you can use utilities in the Linux to inspect that code itself. But if you don't want to do that on your VM, this is nothing but just a plain text replica of the same code out there. So on the left, what you can see is different kernel versions. And that is what I meant in the start, that kernel is always evolving, right? So see, we were this term we are doing at 6.10, right? So I just switched to 6.10, but now you can essentially see that kernel developers are already working on 6.11, right? In project 1, we talked about some LSB version, LTS version, and immediately a new LTS version was released. So things are always evolving. We discussed something today, maybe things have changed in the next kernel version. So it's very important to keep ourselves updated with what is happening. The basic idea never changes. It's how it's implemented is what is changes, right? So to one of the best ways to understand Linux code is this particular website, Bootlin. And we are sorry to say, but there is very less documentation when it comes to kernel development, right? So most of the kernel documentation that you'll see is in the mail archives, where two kernel developers are talking about a feature or a support, and there is the way they extensively talk about. This is the problem of this community. You can say there's less documentation as compared to, I cannot point you to a specific website which has a detailed documentation. And even if it is, for example, in project 3, we gave you some references, right? So yes, yes. So we gave you some bunch of references. Those references are from Understanding Linux Kernel book, but that is 3rd edition, right? When kernel version was at 2.6, right? Now we are at kernel version 6.10, right? So it's very difficult for people to keep up at it as well, right? And that is why you'll see that very less people work in this domain. So if you are working, if you have interest, it's a good sign for you in the future. But yeah, I hope this website was helpful. And yeah, you were having a question.
Yeah, I was just gonna ask if there was a place where we could read about the changes that they make.
No, it's very, to be honest,
mail
it's
archives.
it's very difficult, and we suffer with that as well. Okay, let me look up if I have that website open essentially. Okay, so there is this this website patchworklinux.org. Okay, not to overwhelm you guys, but if you're interested, someone is interested. So what this hosts is a list of all the mailing archives. So for example, if some development happened in Bluetooth device, so you will find all the mailing communications amongst different developers over here. And this is the best way to keep up, with the changes, to understand what's happening with different kernel versions and whatnot. So like CXL is a coming technology, so you'll find mail. That's how we keep up with things. Okay, so I think we are out of time as well.
10 minutes over.
Yeah. So, okay, if you guys don't have any questions, we'll end this meeting. Thank you guys online for joining. Have a good rest of the day, guys.
You too. Thank you. Have
You
a good
too.
weekend.
Yeah.
Thanks.